So I've been putting a ridiculous amount of time into designing this motor controller now, and I'm essentially done the design. I like using my old Dell here for all the CAD work. It's a pretty old machine, but it screams along and does the job really good. I like using it. So I have some of the materials here for the motor controller. I'll just show you what I'm thinking of doing here. So this is, the aluminum here is going to be my heat spreaders and heat sinks. And the copper bars here, of course, are going to be my main conductors. Now what I plan on doing here is, I plan on building it in such a way that the PCB actually doesn't conduct any of the power. Because even if you have a very thick gauge or heavy gauge copper on the PCB, it's still only going to be microns, or at best a millimeter or two thick, whereas you pretty much can't beat solid copper bars. So that's the plan, is to connect all the power devices directly to these copper bars. And these here are 3/16 inch thick by 1 inch wide. They're actually quite heavy, and these should carry my 650 amps no problem at all. And then underneath here I'm going to have these 1.5 inch by 1 inch aluminum bars. Those are going to be attached to the body of the Mosfets, and those are going to draw away the heat. And then of course that is going to be coupled to this plate on the bottom that's going to spread out the heat even more. So it's going to be pretty good, I think. It's always kind of tricky to calculate the thermal characteristics of all this stuff. You'd really need to do a whole bunch of testing on it in order to know for sure, because it's going to be influenced by airflow and how it's mounted and tons of different things like that. So anyway, like I said, I plan on having the PCB conduct almost no current here. So what my plan is you can imagine this sheet of paper here with all these ridiculous calculations on it and circuits. You can imagine this being my PCB. So looking at it from the front, that's going to be the stack up like this, and these copper bars are going to be on top. Now what I plan on doing is I plan on having the transistors, or Mosfets, I plan on having them mounted like this, coming up through the board. So as you can see, the main body part of the Mosfet can be directly bolted to those aluminum blocks under there. And the legs, what I'm actually going to do is I'm going to solder ring terminals onto them, and then I'm going to bolt them directly to the copper bars. So it's going to be as direct a connection as possible. Like I said, the printed circuit board is really going to be there just for spacing of the Mosfets and alignment, and of course all the gate drive stuff and all the other stuff, but nothing of any serious power is going to be going through the PCB. So that's the plan for the mechanical setup, or at least the mechanical setup now. Originally I had planned on making the board in several sections. This would be the control board that I had planned out, and it has a couple connectors on here that would connect up to the power board, which would be next to it. And that was this here, where the power board would sit like this, and it would connect up with this board here. These two connectors here would connect up with these two connectors, and then I planned on having another board just like this connect up again, so there'd be a total of 3 boards connected together like that in a row. Initially I thought that was a good idea, but I changed my design because I realized that was just going to be very fiddly with 3 separate boards like that. It wasn't going to be a very sound construction technique, and it just wasn't the best. So what I decided to do was I decided to scrap that. One of the reasons why I decided to change my mind is because really I couldn't fit as many capacitors on here as I wanted to. That's another tricky thing about this design, is that you don't really ever know how much inductance is going to be in those wires coming into the motor controller. It's really a total crapshoot. So I mean, if you have enough capacitance, you'll be fine, but if you have too little capacitance, then you're going to have those large voltage spikes I was talking about in the last video, and that's going to take out your MOSFETs. So you want to make sure you have enough capacitance, but determining how much capacitance you need is really tricky. It's pretty much near impossible because you can't know what the inductance of your system is going to be. So it's really just a guess. So the best way to go about it, in all honesty, is just to whack on as much capacitance as possible. So, and I realized that with this design I couldn't really put much capacitance on there. It was really the limiting part of this design. So what I decided to do is I changed the design to this. This is the capacitor and control board. So this is the control section. This is the capacitor section, so you can see it's just all capacitors. And that's one board, so that'll be on the top. This is just the same board but the bottom layer, so you can ignore that. And this is the MOSFET board, so this is going to carry the MOSFETs, the copper bars and the aluminum bars, and this is actually going to sit on top of this other board, probably spaced out about 3/4 of an inch is what it's going to be. So basically I'm going to have a 2-board stack up here. There's going to be a bottom board with this that's going to be sandwiched in between these aluminum bars and the copper bars, and there's going to be a top board that's going to have all the capacitors and the control circuitry on it. And it's going to be it's going to look very elegant in a way, because it's going to, if you look at it from the side, it's going to be all a very uniform thickness going all the way down with those capacitors and the ICs and everything on there. So I think it'll just look really nice too. Now, one problem I have, mechanical issue, is that these bars that I got, they're 1 1/4 inches wide by 1 1/2 inches tall. And well, what I really wanted is I wanted a bar that was 1 inch wide by 1 1/2 inches tall. So unfortunately, these aren't the size I wanted. The metal shop didn't have the exact size I wanted. So what I'm going to have to do is I'm going to have to nick off 1/4 of an inch off here. It's going to be a bit of a pain in the ass, but it's got to be done, because the design, I can't accommodate anything wider than an inch there. It's got to be an inch, so or else it's going to start getting in the way of my design, and I can't change my design anymore. I can't widen it at all because it's not going to fit in the bike. So that's how constrained this whole design is. There's a ton of things that depend on a lot of other things, and yeah, it's been tricky. So yeah, what else? So this is the top side of the MOSFET board. So you can see it's just basically a crap ton of copper. There's not really a whole lot else going on there. There's a whole ton of holes for all those ring terminals I was talking about. There's going to be bolts basically just going straight through the board, fastening all those ring terminals to the copper bars here. Now the bottom side of the MOSFET board looks like this. Now this is actually an old printout. These bars you see here are actually the mask that I've left removed. So the solder mask in these square sections here will be gone, and that's why these copper bars can be mounted directly to the board, is because it'll bolt directly to the metal right on the PCB. So this is actually on the top layer now. So this isn't entirely accurate. But anyway, all of the gate drive stuff, as you can see, is right on the board here, right next to the MOSFET. So you can't design it any better than that. With the gate drive circuitry being right next to the MOSFET like that, that lowers the loop inductance of each one of these gate circuits, and just makes for way faster MOSFET switching. So it's gonna be awesome. Now, one thing that I have going on here is you can see these pads here. So initially what I wanted to do is I wanted to connect these two boards together with connectors. But the problem is that the current sensor, it has a hole in it that'll accept a 3/4 inch wide bar, so I have to trim this down a little bit on one end to fit the current sensors. But of course the problem is that it's got to slide on, right? And if I have any connectors in between these boards, then what's going to have to happen is the boards are going to have to separate before I can slide that out, and it's not really going to work very well. So what I decided to do is I'm going to basically free wire these connections here. I'll solder wires into these vias here, and then those wires are going to jumper over to the control board here and be inserted into these spring terminals. So it should provide a really good connection, because I mean you pretty much can't beat wires, and I can change the gauge to whatever I want, and like I said, then what this design allows me to do is it allows me to disconnect the wires on the control board here and then slide the board out, so that these current sensors, which are mounted right here and here, you probably can't see them on here very well. No, you can't. But it allows the current sensor to slide out over those copper bars. Now this was the initial design I had. It had these DC to DC converters here, these slim package ones. The camera won't focus very well there. And they were great initially. Actually, let me take this to the computer. Let's look at this on the computer. I think it'll be much easier. So initially I had designed the board around these converters here on the right. They're really nice in that they're small and they're compact, but the problem is they're only 2 watts, and that became a concern to me because when calculating the amount of power that was going to be required to drive the gates of these MOSFETs, it came pretty close to that 2 watts there. So I was concerned that this converter would be either too stressed, or possibly my load might be higher than the converter can take. And you know, that's the last thing I want in this design, is to be limited by how much gate drive I have. I want this thing to be basically I want to be limiting this thing myself, just to avoid issues with inductive spikes. I don't want this thing to be limited by the components I'm using. And the reason why that came up is because looking at this datasheet here for the synchronous controller, it gives a graph at the end here. Let's see if I can find it. Supply current versus frequency here. This is an important one. So this is actually what the power consumption of the synchronous IC is, depending on what frequency it switches at and what load it's driving. So the MOSFETs I'm using, they're actually about 15 nanofarads, so they're big, and you can figure that out from the datasheet, because what they do on these MOSFET datasheets is they specify a gate charge. So here we have typical gate charge is 151 nanocoulombs. And they specify that at a gate to source voltage of 10 volts. And so you can calculate capacitance from that. Of course, the capacitance is equal to the charge divided by the voltage. So that actually comes out to 15 nanofarads, 15.1 nanofarads, I guess. And that's the typical figure, of course. The max is 227 here. So typically, the MOSFET will be 15.1 nanofarads. So basically, since they don't have a plot on this graph at 15 nanofarads, I kind of have to interpolate this graph a little bit. So you can roughly guess that the load is going to be 1.5 times higher because the capacitance is 1.5 times higher. Of course, energy stored in a capacitor is 1/2 CV squared. So the capacitance is linearly proportional to the energy stored, as long as the voltage remains the same. So if I have a 15 nanofarad gate capacitor there, basically that's going to be 1.5 times the load. Now it's a bit tricky to figure this out because, of course, the synchronous controller has a static load, of course, too. And it looks like it's about 6 milliamps here. So it's going to draw that 6 milliamps no matter what I'm powering here. But So basically, I think I'm going to be switching somewhere around 20 kilohertz. 20 kilohertz, that's this line here. And I think I'm going to be, my capacitive load is going to be around 15 nanofarads, give or take. So you can interpolate from this graph here roughly what power consumption is going to be required. And I think I determined that it's basically going to be somewhere around 12 milliamps. Worst case is what's going to be required. So of course, the thing that's you can calculate. So if each one's going to take 12 milliamps, well, I have 12 MOSFETs in my design. By the way, it's no longer 10. I've decided to make it 12 because it's lowers that on resistance a little bit more, and it reduces the amount of current in each MOSFET. So I've decided on 12. So if each one draws 12 milliamps, give or take, that's 144 milliamps there. That's going to be required for these to drive these MOSFETs at 12 volts. And this is also at 10 volts, by the way. I'm driving them at 12 volts. So I think the supply current will be a bit higher at 12 volts as well, due to that 1/2 CV squared I mentioned. There's more energy there. So basically, it's going to take about 150 milliamps at bare minimum to drive these MOSFETs. And while looking at this power converter here, the model I was using is only good for 167 milliamps. So yeah, it's pushing it way too close there. I really want some overhead on this DC to DC converter to be able to drive those MOSFETs really well. So I just decided on I needed a more powerful DC to DC converter to power these things. So I chose this one instead here, made by TDK Lambda. And the version I'm looking at here is the 12 volt version, which is actually 3 watts. So this is a 2 watt package here. This one over here is a 3 watt package. So it can supply up to 250 milliamps. So it's a fair bit more, and it should be able to, should be more than enough for those MOSFETs. So this was just looking at the synchronous rectification side of things. Now I think the power consumption on the low side MOSFETs is going to be less. But even so, I don't want to have my gate drive limited in any way. So I've definitely decided on using this converter for both the low side and the synchronous MOSFET drive circuits. Now looking at the design here again, so a couple things I had to change. So I changed the DC to DC converters here. I have these 2 bigger TDK Lambda ones now. And I still have that smaller inline one down here to power the control circuitry. And going to those bigger converters, they're a physically larger size as well. Presented a bit of a problem. In the previous design, I actually had these types of fuses here. They're the glass fuses with metal fuse holders. But those are just way too big now. I simply don't have the space anymore for those fuses. And of course I want to maintain those fuses. I want to be able to have each circuit fused to the correct current. And it's also good for testing because you can basically pop the fuse out of the fuse holder, and then with your meter you can probe across it and measure the current. So I really want to be able to do that. So instead of those glass fuses, I've moved to these fuses here. They're a smaller board mount type I found, and they're still socketable, so you can pull them and insert them into a socket. They're just way smaller. Now one thing I've done with the design as well here is that I have LEDs for all of the power rails. There's actually 4 power rails on this thing. So there's 12 volts for the synchronous MOSFETs, there's 12 volts for the low side MOSFETs, there's 12 volts for the control circuitry, and there's 5 volts for the control circuitry. So I wanted everything to be individually fused here, and I wanted everything to be individually indicated by LEDs, because then, let's say a fuse blows, well then my LED for that power rail will go out, and I'll know that I have a problem. What else have I done here? So I mentioned the field wiring aspect of it. So basically there's going to be flying wires in between these two boards here. And I apologize for not having screen capture on this computer, by the way. That's about it. I mean, other than that, without going into all the gory details, without too many other gory details here, this circuit has I mean, I'll show you the schematic for this one. Let's go to schematic. And yes, I'm using dip trace. To be honest, for this particular design, I probably should have used Altium because it is getting quite complex. But I should be able to get the job done here with dip trace. So what I've done here, let's see if I can find it. For the hardware current limiting, this is the circuit. It's basically, this is a comparator here, and I have a resistor divider network here set up to create this voltage, which equals about 500 amps. Now the current sensors are set up in such a way that one is actually going to read negative and one is going to read positive. That's just the nature of the beast, how this thing's set up. So with the battery current limit, it's set up to read negative, and I have that limit set at about negative 500 amps there. Because of course, I don't want this thing to normally trip on hardware overcurrent. I want it to be completely software controlled. I just want this hardware limit in place in case something gets buggered with the software. So I don't want to depend on this, so I'm going to set this quite a bit higher than what the software should control it at. Now, I have an LED on the output here to indicate if there's a fault. And this circuit here, you'll notice there's no hysteresis at all. So like, as soon as the current sensor hits 500 amps, the comparator will cut out this circuit on the output here. This will drop, the voltage will drop here, and this actually goes into a 3-input AND gate, and the third thing that's going into the AND gate is the pulse width modulation signal. So basically, when this hardware overcurrent trips here, it'll keep the pulse width modulation signal from exiting this AND gate here. So very, very straightforward. Now the motor hardware current limit is a bit interesting. So there's actually some feedback here, and what this does is it creates a huge amount of hysteresis. So the comparator, it won't trip until the sensor reads 728 amps, but once it's tripped, it won't untrip. It won't return to its original state until the current has dropped to at least 180 amps. So there's a ton of hysteresis in there. Whereas with the battery current circuit, there's no hysteresis. So basically, as soon as it gets below 496 amps again, this will reset itself, and then it'll allow that pulse width modulation signal to go through. So this isn't really the best, but since the current sensor has to read negative here due to mechanical constraints, that's the best I could do. There's no really easy way to add feedback here without messing something up to create a big hysteresis there. But that'll do the trick. I expect motor current will be the biggest thing that'll be limiting the controller. That'll be hit on a regular basis. So yeah, I have it set at 728 amps. The software limit, of course, is probably going to be 650 amps, so barring any issues, I can always tweak that higher or lower. So that's the design thus far. Now, one trick I always do whenever I'm designing printed circuit boards, which you've probably noticed already, is that I always print out the design. Now, what I always do is I order, I go through the design process. A lot of times you do have to go between your board and your schematic layout quite a few times, because occasionally you run into a mechanical issue, and then it determines that you have to change your electrical schematic in such a way to accommodate that mechanical issue. And of course you have to have your schematic to meet your minimum requirements. So, and sometimes you have to bend the mechanical issues out of the way a little bit to get the job done. Anyway, so what I really like to do is once I'm done the design, I'll print it out like this, and this is at 1:1 scale, by the way. And what I'll do is I'll order all the parts, but I won't order the boards. I'll just order all the parts. I'll get all the parts in, and then what I'll do is I'll manually, you know, go around and I'll check all my footprints here against my parts and just make sure everything matches up. You'd be amazed at how many issues I've avoided just by you know, taking the physical part and placing it on this 1:1 printout here. It's quite hilarious, actually. It's pretty easy to mess up footprints, so it's a really quick and easy thing to check. And of course, we're building a three-dimensional unit here, and this is only a two-dimensional design. So a lot of times you'll realize issues with your design by taking the physical components and trying to place them where they're meant to go. You'll be like, oh, this Mosfet here doesn't actually fit. There's not enough height there, or some other issue, right? So yeah, this is just one thing I do to help avoid any issues with the PCB design, because the last thing you want is to order your PCB, wait a week or two to get it, and then you know, spend money on it, and then find out that something really stupid in your design is going to keep you from being able to build it and have it function correctly. So yeah, just one tip for me. That's one thing I always do whenever I'm designing a PCB, is I always order all the parts, and then I'll manually go and place them on my printout before I even order the boards or anything like that. So one other thing that I'm going to have a potential issue with here, which I'm not sure how to deal with yet, is insulation. So of course the backside of these Mosfets, this is actually just a bipolar transistor, a TO247 size transistor, the same size I'm going to be using for this design. Of course, the backside of the Mosfets are typically connected to the drain pin, the die inside there. So I can't just go and mount these right on the metal here, or I could, but I'd have to do one thing or the other. So obviously one of these, this set of Mosfets up here, the backside is going to be connected to battery plus, and the backside of these Mosfets here are going to be connected to motor minus. So basically I can't have these two connected, or else they'll short out, and additionally I can't have the plate here connected to anything, because the last thing I want is to mount this thing on my bike and then have some kind of weird issue where battery plus or motor minus is connected through to the chassis on my bike. That'd be that'd be a big safety concern. So I have two options here. I could put an insulative pad in between the Mosfet and the aluminum bar here. Now that's going to do the job, of course, with isolation, but the thermal pad is going to limit the amount of heat transfer I'm going to get to this metal bar. Or alternatively, because the only thing this metal bar is connected to is the Mosfets and this bottom plate here, what I could do is I could put an insulator in between the metal plate here and this metal bar. Now I think that's probably what I'm going to do, because if I have these Mosfets directly connected to the heatsink here with some thermal grease or whatnot, I'm going to get way better thermal performance, I think, especially since the bottom of this bar is going to have much larger surface area than the contact area on these Mosfets here. So by having an insulative sheet in between the plate and the bar here, that surface area is much bigger. I think overall the thermal performance of the system will be better if my thermal sheet is in between these two pieces of metal here instead of between my Mosfet and the metal. And as well, it'll keep the junction temperature of the Mosfet lower by having a more direct connection to metal like that. As well, another thing that'll be good is that since these leads will be basically bolted directly to these copper bars, that'll be another additional path for heat to travel. But of course it won't be as good as the connection to the actual body of the MOSFET. That's where all the heat is going to be generated. So I think the next stage here is going to be ordering all the parts. I'm going to be putting an order through for all the parts this weekend, and I'll get all those parts in this week, and then hopefully I'm just going to confirm all my dimensions here, make sure there's no mechanical issues, and of course electrical issues, and then I'll probably be ordering the PCBs the end of next week. So things are progressing quite quickly here, and I'm quite happy about the way it's going. So yeah, until next time.